Oxidation and reduction reaction. So first is, what is oxidation? Oxidation is the process which involves the addition of oxygen or any electronegative element or the removal of hydrogen or any electropositive element. Next is, what is reduction? Reduction is a process which involves the addition of hydrogen or any electropositive element or the removal of oxygen or any electronegative element. To understand more of this, here are the classical idea of oxidation and reduction reaction. An oxidation reaction involves addition of oxygen. The chemical equation shows the oxidation of carbon, in which carbon reacts with oxygen to produce carbon dioxide. Number 2, addition of electronegative element. In this chemical equation shows the oxidation of iron. Iron reacts with sulfur to produce iron sulfide. Number 3, removal of hydrogen. The chemical equation shows the oxidation of sulfide. Hydrogen sulfide reacts with bromine to produce 2 molecules of hydrogen bromide and sulfur. And number 4, removal of electropositive elements. The chemical equation shows the oxidation of iodine. 2 molecules of potassium iodide reacts with hydrogen peroxide to produce iodine and 2 molecules of potassium hydroxide. And the oxidizing agent in these examples are oxygen, sulfur, bromine, and hydrogen peroxide. The other part of the classical idea is the reduction reaction, in which involves number 1, addition of hydrogen. The chemical equation shows the reduction of nitrogen. Nitrogen reacts with 3 molecules of hydrogen to produce 2 molecules of ammonia. Number 2 is the addition of electropositive element. The chemical equation shows the reduction of mercury chloride. 2, chloride reacts with mercury to chloride to produce tin chloride and mercury chloride. Number 3, removal of oxygen. The chemical equation shows the reduction of zinc oxide. Zinc oxide reacts with carbon to produce zinc and carbon monoxide. Number 4, removal of electronegative element. The chemical equation shows the reduction of ferric chloride. 2 molecules of iron 3 chloride reacts with hydrogen to produce 2 molecules of ferrous chloride and 2 molecules of hydrogen chloride. Oxidation and reduction in terms of electron transfer. So this is the most commonly used definition of oxidation and reduction and most widely applicable. In this case, oxidation is the loss of electrons and reduction is the gain of electrons. A very clever mnemonic to remember this concept is oil rig, where oil stands for oxidation is loss and rig stands for reduction is gain. So, to fully understand what is oxidation and reduction reactions, oxidation and reduction reactions are always interlinked. So, bawal po sila maghiwalay kasi yung electrons are neither created nor destroyed in a chemical reaction. At base po sa sinabi ko, oxidation and reaction are always occur in pairs, meaning it is impossible to have one without the other. Example is magnesium gets oxidized by losing 2 electrons to oxygen, which gets reduced by accepting 2 electrons from magnesium. So vice versa lang po. Yung binawas ng magnesium na electrons to oxygen ay pinapalitan po by accepting 2 electrons from magnesium. And since oxidation and reduction cannot occur individually, they as a whole are called redox reaction. The reactant that oxidizes the other reactant is called the oxidizing agent, and the reactant that reduces is called reducing agent. And the following steps ay makakatulong kung paano mas madaling maintindihan ang oxidation and reduction reactions. An oxidizing agent oxidizes the other reactant. This means that the oxidizing agent is getting reduced. Base nga po doon sa oil rig, yung oxidation is loss, then reduction is gain.
Balancing redox reaction using the change in oxidation number method. An oxidation reduction or the redox reaction is a type of chemical reaction in which the oxidation states of atoms are changed. Redox reactions are characterized by the actual or formal transfer of electrons between chemical species, most often with one species undergoing oxidation while another undergoes reduction. And one way to balance redox reaction is by keeping track of the electron transfer using the oxidation numbers of each of the all atoms. For the oxidation number change method, start with the unbalanced skeleton equation. Example of this is the reaction of iron oxide with carbon monoxide. First step in balancing redox reaction is assign oxidation numbers to each of the atoms in the equation and write the numbers above the atom. Second step is identify the atoms that are oxidized and those that are reduced. In the above equation, the carbon atom is being oxidized since its oxidation increases from +2 to +4. The iron atom is being reduced since its oxidation number decreases from +3 to 0. Next step is use a line to connect the atoms that are undergoing a change in oxidation number, and on the line, write the oxidation number change. The carbon atom's oxidation number increases by 2, while the iron atom's oxidation number decreases by 3. As written, the number of electrons lost does not equal the number of electrons gained. In balanced redox equation, this must be equal. So, the increase in oxidation number of one atom must be made equal to the decrease in oxidation number of the other. Next step is use coefficients to make the total increase in oxidation number equal to the decrease in oxidation number. And in this case, the least common multiple of 2 and 3 is 6. So the oxidation number increase should be multiplied by 3, while the oxidation number decrease should be multiplied by 2. The coefficient is also applied to the formulas in the equation. So A3 is placed in front of the carbon monoxide or the CO and in front of the CO2. A2 is placed in front of the iron or the Fe on the right side of the equation. The Fe2O3 does not require a coefficient because the subscript of 2 after the Fe indicates that there are already 2 iron atoms. Last is check the balancing for both atoms and charge. Occasionally, a coefficient may need to be placed in front of a molecular formula that was not involved in the redox process. In the current example, the equation is now balanced.
Reaction occurring in different parts of the cell. What is an electrochemical cell? An electrochemical cell is a device that can generate electrical energy from the chemical reactions occurring in it, or use the electrical energy supplied to it to facilitate chemical reaction in it. Electrochemical cells generally consist of a cathode and an anode. Electrochemical cell has two types, the galvanic and electrolytic cell. Cathode, denoted by a positive sign since electrons are consumed here. A reduction reaction occurs in the cathode of an electrochemical cell. Reduction reaction happens when an atom gains one or more electrons during a chemical reaction. That means that its oxidation number decreases. This is because an electron has a negative charge. Thus, when an atom gains an electron, it gains a negative charge which decreases the oxidation number. Anode, denoted by a negative sign since electrons are liberated here. An oxidation reaction occurs here. Oxidation reaction is the combination of a substance with oxygen, a reaction in which the atoms in an element lose electrons and the valence of the element is correspondingly increased. Primary and secondary cells. Primary cells are basically use and throw galvanic cells. The electrochemical reactions that take place in these cells are irreversible in nature. Also, secondary cells, also known as rechargeable batteries, are electrochemical cells in which the cell has a reversible reaction. The cell can function as a galvanic cell as well as an electrolytic cell. Galvanic cell or voltaic cell. Chemical energy is transformed into electrical energy in these electrochemical cells. The redox reactions that take place in the cell are spontaneous in nature. Electrolytic cell. Electrical energy is transformed into chemical energy in the cells. An input of energy is required for the redox reaction to proceed in the cells. The reactions are non-spontaneous.
Reduction potential, a measure of how much an element intrinsically wants to be reduced. Some compounds in the earth wants to gain electrons, they want to be reduced, while some compounds wants to lose electrons, they want to be oxidized. The unit for reduction potential is volts. As you can see on the table, you can see the standard reduction potentials. Standard reduction potentials can be positive or negative. So, chlorine has the most positive, so it means chlorine wants to be reduced the most. Sodium has the smallest reduction potential, so it wants to be reduced the least. A greater reduction potential is a more positive value. In reduction potential, there is a gain on electrons. Oxidation potential. Oxidation potential is very similar to reduction potential, except that it is the opposite. Instead of how much an element wants to be reduced, the oxidation potential is the measure of how much an element wants to be oxidized. So in the table, sodium cation has a reduction potential of 2.71 volts. So if you do the opposite, sodium atom has an oxidation potential of negative 2.71 volts. The more positive the oxidation potential, the more element wants to be oxidized. So in oxidation potential, the element loses electrons. Cell potential. The cell potential of a cell is the sum of the oxidation potential of the element being oxidized and the reduction potential of the element being reduced.
Standard cell potential. Before we proceed to the example, let's first take a look at this table, the standard reduction potential table. Ang table po ito ay hindi kompleto, kaya feel free to search na lang po sa Google ng standard reduction potential table. Pero for now, magagamit po natin itong table para sa examples mamaya. Proceed tayo sa first example. Calculate the standard cell potential of this reaction. To calculate this, the first step is to split the reaction into two half reaction. So paghiwalayin po natin sila. Sa paghiwalay po natin, i-copy lang po natin ang zinc, katulad po nito. Ihiwalay po natin siya sa copper. Tapos ang copper naman po, ihiwalay po natin ang copper sa zinc. Yan. Napapansin nyo na wala na siyang halong copper. Tapos ito, wala na siyang halong zinc. Naiwalay na po natin sila. Second step is to add the electrons to balance the charges. Unahin natin ang zinc. Napapansin nyo na ang zinc ay may charge na 2. Mag-iisip po tayo ng number na pag in-add po natin sa zinc na ito ay magiging ganito po ang kakalabasan. So dahil 2 po ito, mag-add tayo ng 2 electrons para maging ganito. Tapos sa copper naman. Sa copper, dahil 2 ulit, edi 2 ulit ang idadagdag natin na electrons para maging ganito ang kalabasan. Then napapansin nyo na ang electrons ng zinc na ito ay nasa right hand side. Kaya ang tawag po sa iya is oxidation. At ito naman dahil nasa left hand side ang electrons, ang tawag po sa iya is reduction. Dahil na-add na natin ang electrons, proceed po tayo sa third step. Determine the voltage of each of these half reaction. To determine the voltage, hanapin lang po natin ang zinc sa table ng standard reduction potential. Ito po ang zinc. May voltage po siyang negative 0.76 volts. At dahil oxidation nito, kailangan po natin siyang ma-flip or maiba ng posisyon para maging reduction. Pag ginawa natin iyon, ang volts niya ay magiging positive 0.76 volts. Tapos, dahil reduction na ito, hanapin na lang po natin ito sa table. Ang copper ay may volts na 0.34 volts. Katapos po natin ma-determine ang voltage ng half reaction na ito, ang fourth step po is to add the reactions. I-add lang po natin sila. Notice that ang dalawang electrons ay makakancel dahil magkaiba po sila ng position. Ito po ay nasa right hand side, ito po ay nasa left hand side. Kaya po makakancel po ang dalawa. Ganun lang po kasimple ang standard cell potential. Ang final answer po natin is positive 1.10 volts. Another example. Calculate the cell potential of a galvanic cell that uses the two half reactions shown below. In galvanic cells, the standard cell potential has to be positive. So, the first step is to observe the given half reactions. Observing it, we notice that the two electrons have different values. In silver, the electrons is 1. And in magnesium, the electrons is 2. And then, if we add these two, the answer is not positive. It should be a positive answer. And then, we notice that the two electrons here are both on the left-hand side. So if the answer is positive, we need to change this reaction. Second step, reverse the half reaction so that the electrons aren't on the same side and the result should be positive. So, ito po ang i-reverse natin. Yan. Pag-reverse po nito, ang magnesium ay ilalagay natin sa left-hand side. Tapos, ang magnesium ion ay ilalagay natin sa right-hand side at ang dalawang electrons. Tapos, dahil i-reverse natin ito, itong negative 2.37 volts ay magiging positive 2.37 volts. Notice that we have two electrons here, and then the silver has only one electron. So to fix this, we need to multiply two electrons in this half reaction. If we multiply 2, notice that this doesn't change at all. It will remain the same as before. Then, after we multiply it by 2, let's proceed to the third step. The third step is to add the reactions. Note that this is a redox reaction. So one reaction must be oxidation and one must be reduction. So the electrons cannot be on the same side. It simply does not work that way. If we add the reactions, notice that the two electrons here are cancelled. And then we have magnesium here, 2 silver here, and then 2 silver and magnesium ions here. And then we add these two. The cell potential of this is positive 3.17 volts. Let's proceed to the next example. Calculate the cell potential of the electrolytic cell according to the reaction shown below. Note that the cell potential of an electrolytic cell can be positive, negative, or zero. Kung sa galvanic cell, positive lang, dito pwedeng maging positive, negative, or zero. First step is to split the reaction into two half reactions. Then, the second step is to add the electrons to balance the charges. Kung nahihirapan kayong mag-add ng electrons, pwede nyong tingnan ang itong table, Standard Reduction Potential Table. Diyan na po nakalagay kung ilan electrons ang meron dito. So pag na-add na po natin ang electrons, let's proceed to the third step. Determine the voltage of each of these half reactions. So to determine the voltage, titingnan lang po natin ang Standard Reduction Potential Table. Hanapin po natin ang iodine. Ang iodine po ay nandito. Meron po siyang positive 0.54 volts. So kakopyahin po natin siya. At dahil nasa right hand side siya, it is oxidation. Bawal po itong maging positive 0.54 kasi po ang table po natin is for reduction, hindi po siya for oxidation. So, ang 0.54 ay gagawin lang natin negative 0.54 volts. At ito, dahil nasa left hand side na talaga ang electrons niya, hanapin lang natin ang aluminum. Ang aluminum ay may negative 1.66 volts. Kaya, kakopyahin lang po natin siya, negative 1.66 volts. After determining the voltage of each of the half reactions, let's proceed to the fourth step, add the reactions. Notice that the electrons here have different values. To fix this, we need to find the least common multiple of 2 and 3. The least common multiple of 2 and 3 is 6. So we need to multiply 3 here and 2 here. If we multiply it by 3 and 2, it will result to 6 iodine and 2 aluminum. And then, notice that negative 0.54 and negative 1.66 is unaffected by the 3 and 2. So, these two will remain the same. Since the two electrons have the same value, we can now add the two reactions. So, if we add the two reactions, it will result to negative 2.2 volts. Ganyan lang po ang pag-calculate ng cell potential ng electrolytic cell.
Relate the value of the cell potential to the feasibility of using to cell generate an electric current. Key points. The cell potential of an electrochemical system is a collection of electrical potential different across all the interfaces in an electrochemical cell, regardless of current passages through the cell. An external source of electrical energy is used to generate a potential difference between the electrode that forces electrons to flow. Cell potential. The cell potential of an electrochemical is the potential difference occurring between the two electrodes of the cell and arises due to the transfer of electrons through the external circuit of a cell that has not reached equilibrium. Redox reaction. A redox reaction occurs when electrons are transferred from a substance that is oxidized to one that is being reduced. The reductant is the substance that loses electrons and is oxidized in the process. The oxidant is the species that gains electrons and is reduced in the process. The associated potential energy is determined by the potential difference between the valence electrons in atoms and different elements. In galvanic cell, the Gibbs free energy is related to potential by delta G naught cell is equals to negative N F standard cell potential cell. In galvanic cell, where spontaneous redox reduction drives the cell to produce an electric potential, the change in Gibbs free energy must be negative. This is the opposite of the cell potential, which is positive when electrons flow spontaneously through electrochemical cell. The relationship between delta G naught and standard cell potential is given by the following equation. Here, N is the number of moles of electrons and F is the Faraday constant, 96,485 coulombs mole, as such as the following rules apply. If standard cell potential is greater than 0, the process is spontaneous or galvanic cell. If standard cell potential is less than 0, then the process is non-spontaneous. The voltage must be supplied as in an electrocyclic cell, two types of electrochemical cells, galvanic cells and electrolytic cells. The oxidation half reaction occurs at one electrode, the anode, and the reduction half reaction occurs at the other, the cathode. When the circuit is closed, electrons flow from the anode to the cathode. The electrons are also connected by an electrolyte, an ionic substance or solution that allows ions to transfer between the electrode compartments, thereby maintaining the system's electrical neutrality. The potential difference between the electrode causes electrons to flow from the reductant to the oxidant through the external circuit, generating an electric current.